Hello dear students, I am Dr. Jagdisha. Today we discuss some few concepts of groups in the paper Algebra and Differential Equations of the third sem BSc Mathematics. In the previous session, we have learned the definition of a group and we have also discussed various examples of finite and infinite groups. Along with that, we have derived some of the properties of groups. Today, we are going to learn some of the few definitions in group theory. First of all, let us define what is meant by permutation. A permutation is a one-to-one mapping of a finite set S onto itself. You can understand this with the help of an example. Consider S is equal to 1, 2, 3, which is a finite set. So we define a mapping or relation from F from S to itself by this way. You can define in any manner. I have defined it as 1 is mapped onto 2, 2 is mapped onto 3, and 3 is mapped onto 1. So this is one of the mappings. I can represent this mapping in the form of a matrix as below. That is, in the first row of the matrix, we write the elements of S as it is, 1, 2, 3. In the second row, we write their images according to the mapping which we have defined above. So here 1 is mapped onto 2. We have written like this. 2 is mapped onto 3. That is, image of 2 is 3. 3 is mapped onto 1. Therefore 3's image is 1. In the first row, we write the elements of S. In the second row, we write its images. So this type of matrix is said to be a permutation. Actually, the number of elements in that particular set S is nothing but the degree of the permutation. So in our example, S contains 3 elements, 1, 2, 3. Therefore, its degree is nothing but 3 itself. Let us move on to the next definition, what is called as identity permutation. The identity permutation I on a set S which contains distinct elements onto itself is called as an identity permutation of degree n. Means what? Consider a matrix which contains first row and second row as same. That means 1 is mapped onto itself, 2 is mapped onto itself, 3 is mapped onto itself. That means we should define the mapping or the function in such a way that the element should have the image as itself. Therefore, the first row and second row will be the same. So these type of permutations are said to be identity permutation. Next definition. When do we call the two permutations are said to be equal? What to call it as? Equality of two permutations. Consider any two permutations F and G on a set S. So those two permutations are said to be equal if f of x is equal to g of y for all xy belongs to S. That means the image of x in F must be is equal to the image of y in G. Look at this example. We have taken the permutation F in this way, means 1 is mapped onto 3, 2 is mapped onto 1, 3 is mapped onto 2. This is the permutation F. And the permutation G will be having the elements as 2 is mapped onto 1, 1 is mapped onto 3 and 3 is mapped onto 2. So observe both F and G here. In F, 1 is mapped onto 3, I said. In G is also 1 is mapped onto 3. In F, 2 is mapped onto 1. In G is also 2 is mapped onto 1. Similarly, in F, 3 is mapped onto 2 and it is the same in G as well. That means the images of F and G are one and the same. Hence, the permutations F and G are said to be equal. Next, we define inverse of a permutation. Let F be a permutation of degree n defined on a finite set S which contains n elements. As we know, F is a one-to-one mapping of S onto itself. Therefore, its inverse exists. Means you contain S as the elements 1, 2, 3 and define the mapping F or the permutation F as 1 is mapped onto 2, 2 is mapped onto 3, 3 is mapped onto 1. So when you write the inverse permutation, we should interchange the rows. That means the second row in F should be put it as the first row in F inverse. And the first row in F should be put it as the second row in F inverse. That means the rows of F should be interchanged to get F inverse. So this is said to be an inverse permutation. Next, the product of two permutations. Let F and G be two permutations on S which contains n distinct elements. Since F and G are one-to-one and onto, we can define S on S the product. The product is also called as the composition. So it can be denoted as F composition G. We read it from the right side. F composition G. G composition F. So F composition G, we simply call it as the product GF. G composition F, we call it as the product as FG. So we define this product or composition as below. F composition G of X will be G of F of X. And G composition F of X will be F of G of X. So this definition is important to solve the problems in composition or product. So as I said, F composition G is denoted as simply GF and G composition F is denoted as FG. Let us understand the composition of the product with the help of an example. Consider a set S which contains three distinct elements, which is a finite set 1, 2, 3, and let us define the two permutations F and G as given here. So consider the product here G composition F of 1. So G composition F of 1 is defined according to the definition as F of G of 1. So first of all, what is G of 1? We have to take the permutation G and look for one's image. G of 1 means one's image. What is one's image in G? One's image is 3. So G of 1 is 3. Next, what does F of 3 means? We have to look for F here and write the 3's image. 3's image in F is itself, that is 3. Therefore, G composition F of 1 is equal to 3. Similarly, you can find G composition F of 2, you will get 1. G composition F of 3, you will get 2. Hence, the product FG, I can write it as 1 is mapped onto 3 as we have seen above, and 2 is mapped onto 1, I have written it here, and 3 is mapped onto 2. That is this. In a similar way, you can find product GF or F composition G, we get this result. Look at both product FG and GF. In FG, we have 1 is mapped onto 3. In GF, 1 is mapped onto 2. It's different. 2 is mapped onto 1 in FG, but here 2 is mapped onto 3. That is also different. Again in FG, 3 is mapped onto 2, but whereas in GF, 3 is mapped onto 1. So when you look at the mappings of the products FG and GF, the images of the mappings are totally different. Therefore, FG is different from GF. Hence, you can say that FG is not equal to GF. That means the composition of G to F and F to G are not same. I can say in the set S is equal to 1, 2, 3, the product of F and G is not commutative. That is, FG is not same as GF. Let us move on to the definition of a symmetric group. Consider a finite set S which contains n distinct elements. Now, out of this set S, construct possible permutations that you denote it as Sn. So what is Sn here? Sn is the set of all permutations in the finite set S. So if Sn is a group, then is said to be a symmetric group of the set S of degree n. Let us note some points as below. The number of elements in Sn will be n factorial. That means the set of all permutations of a set S always contains n factorial elements. That is n factorial. The group Sn is a non-abelian group. So what does it mean? Sn contains the set of all permutations of a set S. In the permutation Sn, the product or the composition is not commutative. So since Sn does not satisfy the commutative property, we say that it is a non-abelian group. That we have seen in the previous example, in the previous slide. Also, any subgroup of Sn is called a permutation group of order n. Here n is nothing but the order of the permutation group Sn. Let us take up one more example. Consider S is equal to the elements 1, 2, 3, which is a finite set. So let us write the permutation group of S 1, 2, 3. So as we have seen in the previous slide, one of the note says the permutation group of S 1, 2, 3 will contains n factorial elements. So how many elements S has? 3 elements. Therefore, our S3 will contain 3 factorial permutations. That is 3 factorial elements. That is 6 permutations you can write it as. So let us see how to write the permutations of S, possible permutations of S. So P naught, what did we do? The P naught is an identity permutation. 1 is mapped onto 1 itself, 2 is mapped onto 2, 3 is mapped onto 3. Go for the next permutation P1, fix 1 to 1, change 2 to 3, 3 to 2. Similarly, in P5, fix 2 and 1 is changed to 3, 3 is changed to 1. And in P2, fix 3, 1 is changed to 2, 2 is changed to 1. And in P3 and P4, we have rotated the elements 1 to 2, 2 to 3, 3 to 1. In P4, 1 is changed to 3, 2 is to 1, 3 is to 2. So these are the possible permutations of S3. That means there are total 6 permutations. Therefore, the set S3 will have 3 factorial, that is 6 permutations. And we can show that, as we have said above, any of the permutations you take, their product will not satisfy the commutative property. That means it is said to be a non-abelian group. That means F composition G is not same as G composition F. Here you can take any P0 and P5, you check for the compositions. P5 composition P0 and P0 composition P5 you can check, for example. It is not same, it will not be same. Therefore, it will not satisfy commutative property. Since it does not satisfy commutative property, we say that it's not an abelian group. Let us move on to the next definition, transposition of a permutation. So, any permutation F is said to be a transposition. It interchanges two numbers and the others as fixed. Look at directly the example F here. You can understand still better. 1 is fixed as 1, 2 is fixed as 2, 3 is fixed as 3, 4 is fixed as 4. 5 is mapped onto 6, 6 is mapped onto 5. That means only we have changed the images of 5 and the 6. That means 5 is having the image as 6, 6 is having the image as 5. The other elements, 1 will have the image itself, 2 also same, 3 also same, 4 also same. That means we interchange two numbers 5 and 6, leaving the other numbers 1, 2, 3, 4 fixed. This type of permutation is called as a transposition. Now, what is meant by a cyclic permutation? We define it now. That means in any set, say Sn, the permutation F is said to be a cyclic permutation if it satisfies this way. That means N1 is mapped onto N2, N2 is mapped onto N3, N3 is mapped onto N4, N5 is mapped onto N5, N5 to N6, N6 to N7, etc. etc. The last element Nk is mapped onto the first element. Then that is said to be a cyclic permutation. That means a cycle maps N1 onto N2, N2 onto N3, and finally Nk onto the first element N1 itself. The other elements remains fixed. So this type of permutation is said to be a cyclic permutation. Look at the example which is given below. You can understand this cyclic permutation by using this example. In this permutation, 1 is fixed, 4 is fixed. These two elements are fixed. And look at the other things. 2 is mapped onto 5, 5 is mapped onto 3, 3 is mapped onto 2. That means 2 to 5, 5 to 3, and 3 to 2. This is said to be a cyclic permutation. Other than 2, 5, 3, the other two elements, what are the other two elements? 1 and 4 are fixed. So in this permutation F, we have a cycle, namely 2, 5, 3. This cycle 2, 5, 3 can also be rotated and rewritten as 5, 3, 2 or 3, 2, 5. That is by rotating the cycle. So that's it in this session. Let us summarize what we have learned so far. In this session, we have learned some of the definitions as permutation, identity permutation, equality of two permutations, inverse of a permutation, product, it's also called as composition, a symmetric group, the transposition, and also the cyclic permutation. I hope you understood these definitions well. Thank you, students.